Good morning to everybody. In our previous class, we have defined graph, and then we defined the degree of the vertex. The degree of the vertex, we defined that the number of edges incident to it. Now here you are seeing a graph in which there is a speciality in degree of vertex. Every vertex is of the same degree, and that is 3. So this kind of graph, we say that a regular graph if the degree of the vertex is constant, and if the constant is k, then we say that it is a k regular graph. So this Peterson graph is a k regular graph, and where 3 regular graph where k is 3. Now I will describe you that what is basically the construction of Peterson graph. But I just note to you that Peterson graph is not only an example, it is very much important by forming various counterexamples to various theorems. So we will come again and again to Peterson graph to produce some counterexamples to many theories of graph theory. First, let us see that what is basically a Peterson graph and how it is constructed. From let I5, you just start reading from there. From this position, that there are suppose 5 numbers. I am taking 1, 2, 3, 4, 5. And I am taking some 2 sets of these numbers, that is 2 element subsets of this number, and naturally this will be 10, 5 choose 2. So you see that there are all 2 element subsets of this set of 5 elements, 1, 2, 1, 3, 1, 5 and so on up to 4, 5. Now I am declaring that all these 2 sets or 2 element subsets of these 5 elements, they are the vertices of the graph. And what is the adjacency rule? How we will form an edge between 2 vertices? That is, if there is, you see that if they have an empty intersection, then we will join by them an edge. So I am going back to the graph. You just remember the definition. All the elements are of 2 subsets of these 5 set elements, and these are the vertices, and we will join 2 vertices if they are disjoint. So let us take another picture where this presentation is there. Now you see clearly that the representation of the vertices of the Peterson graph, this for convenience we are writing just the numbers side by side, not giving the parenthesis and comma to just make it convenient figure. Now you see that 1, 2 and 1, 3 has a common element 1. So there is no edge between 1, 2 and 1, 3, but 1, 2 and 3, 5 have no common element, and they are disjoint, and so they are joined by an edge. Now interestingly, you note that that Peterson graph, this is of 10 vertices, and this is of how many edges are there? এবার সেখানে 10টা ভার্টেক্স আছে, প্রত্যেকটা ভার্টেক্সের ডিগ্রি 3, তাহলে 15টা এজ হলো কেন, 30টা হলো না কেন? অ্যাকচুয়ালি আমার এজগুলো তো আনডাইরেক্টেড, মানে কোনো একটা ভার্টেক্সের সঙ্গে আরেকটা ভার্টেক্সের এজ আছে, মানে সেই সেকেন্ড ভার্টেক্সের সঙ্গে ফার্স্ট ভার্টেক্সের এজ আছে। ফলে আমি যদি ডিগ্রিটা সাম করি, অবভিয়াসলি আমাকে বাই 2 করে নিতে হবে, যে কারণে 30/2 আমাদের 15টা এজ আসছে। আচ্ছা, কতগুলো প্রপার্টি এখানে নোটিস করো। দেখো, ফার্স্ট অফ অল যে ডিগ্রি প্রত্যেকের যে 3, এটা আমরা কিভাবে প্রমাণ করতে পারবো যে অ্যাকচুয়ালি দ্য ডিগ্রি ইজ 3, বিকজ উই আর টেকিং 5 এলিমেন্ট সেট and one vertex is represented by two element subsets, so three other elements are remaining. Now the adjacency relation, that the set has to be disjoint from it. So there are three elements, three numbers which are not included in these two set. So, and they can be paired in 3C2, that is 3 choose 2, three ways. So every vertex must have the degree 3 and it is constant for the whole graph, so it is a three-regular graph. So many other properties you can see for the graph. Some are listed here. These are easy to understand. You see that the result, theorem 1.1.1, that number of vertices is 10. That is obvious because I am taking two sets from the 5 set. So 5 choose 2 is 10. Every vertex has exactly 3 adjacent vertices that I have just explained. And by definition, then it becomes three-regular graph. The graph has no loops or parallel edges, that already defined that we in the definition. And finally, what is saying that you see the last property, that u and v are if u and v are non-adjacent vertices, then there exists only one vertex w, such that w is adjacent with both u and v. As you see that 1, 2 and 1, 3 are non-adjacent, and you see 4, 5 is the unique vertex that is adjacent to both 1, 2 and 1, 3. And no other vertex is commonly adjacent to 1, 2 and 1, 3. So it is a unique vertex that is adjacent to 1, 2 and 1, 3. And that you can notice for any two non-adjacent vertices, for example, 1, 2 and 2, 4, 3, 5, right? And you see that no other vertices are common to them. So now can you prove it generally? First we note that when the two vertices are become non-adjacent, they are becoming non-adjacent if they have common elements. But they cannot have both the elements common, otherwise the vertices will be same. And so they have exactly one element common. And since they have exactly one element common, so they are covering exactly three elements. So only two elements are remaining to represent another vertex. So that particular vertex is uniquely adjacent to both of them. Since already we have taken three elements, so only two elements are remaining, and you can only form one vertex by them, and so that vertex is uniquely adjacent to both of them. So this is the first preliminary some observation that we did for Petersen graph. Later on we will observe many other things, and as I told you, the Petersen graph will be a very good counterexample to many of the results. For example, we will learn later on, but you can see that there are some cycle-like structures, like you see that this starting from 1, 2, 4, 5, 2, 3, 1, 5, 3, 4, and coming back to 1, 2, you get some cycle-like structure, and also you get another cycle in the star form in between. That is, if you start from say 1, 4, then 2, 5, 1, 3, 2, 4, 3, 5, and 1, 4. We will define cycle and so on in our later on. So, but however, you see that there are two cycles, and you can not see here any fourth cycle. That is, any 4 vertex are forming cycle or any 3 vertex are forming cycle, that you are not seeing here. Because you can have other cycles like you see that 1, 2, 3, 5, 1, 4, 2, 3, 4, 5, and 1, 2 again. So this is another cycle that you see 1, 2, 3, 5, 1, 4, 2, 3, 4, 5, and 1, 2 again. That is another cycle. But this is again a 5 cycle, that is a 5 length cycle. There is no 3 or 4 length cycle. In this case, we have a graph parameter that is called girth, that is minimum length of a cycle, and that Petersen graph has minimum length of the cycle 5. So this is another property I am just describing now. Later on we will study that. Now we switch on to another class of graphs, or another example of graph, that is called the cube graphs. Then what is the cube graph? You see it is another representation. The cube graph is basically the graph that in the 3 dimension you can say like a box, and we also say it is a 3 cube. If it is of we are taking some k, then we can call it is a k cube, and you can represent in k dimensional box also. However, so here you see that we have a commutatorial representation. What is the representation? Suppose I am taking all possible 3 length binary string. What is a binary string? Binary string is nothing but a sequence of zeros and ones. So, for example, here you see that it is 0, 0, 0. That I am again, we are just omitting the parentheses and the commas. So, we are just making it 0, 0, 0, but strictly speaking it is a sequence. 0, 0, 0 is a sequence. It is not a set. You please remember it here, it is not a set. It is not unordered. It is ordered. The first place of it is a finite sequence of 3 length. For first place is 0, second place is 0, the third place is 0, that is 0, 0, 0. However, so obviously there are 3 places and the place value can be 2. So 2 cube, that is 8 numbers, can be found by this. So there are 8, exactly 8 3 length binary string. So that is our vertex set. So we get 8 vertices here. So and the adjacency here we make the opposite kind of the Petersen graph. Here we make the adjacency if there is a common something, but here there may be common many things because here the representation is by 3 elements. So we make the adjacency in such a way that they are differing in exactly one place, that is they are common in 2 places. They are differing in exactly one place, that is they are common in 2 places. Look at the 0, 0, 0 and 0, 0, 1. You see that both the first 2 zeros are common and it is differing in the 3rd place. So they have an edge between them. But if you look at 0, 0, 0 and 0, 1, 1, then you see that 0, 0, 0 and 0, 1, 1, then you see that it is differing 2 places. Only 0 is common, in one place it is common, but it is differing in 2 places. So there is no edge between it. For example, 0, 0, 0 and 1, 1, 1, they are differing in all 3 places. They are differing in all 3 places, and so there is no edge in between them. So our edge relation is nothing but that they should differ exactly at one place. So you see that there is an edge here, there is an edge here, and as before, since there are 3 places, so differing in one place, that means there are 3 cases. It may differ in the first place, it may differ in the second place, it may differ in the 3rd place, and inputs are only 2, 0 and 1. So differing means if it is not 0, it must be 1. If it is not 1, it must be 0. So differing means here just the opposite. So we will have again a 3 regular graph, but this is different from the Petersen graph. Here you see that it is different because the structurally you see there are many 4 cycles. Actually for every 6 sides you are getting a 4th cycle, but in the Petersen graph there was no 4th cycle, and so these graphs are not isomorphic. They are different graphs. They are not the same graph. So but you are getting that for both the graphs degrees are same for every vertex, and degrees are constant also for every vertex, and that is 3. So these are 2 typical example of graphs I am just showing. As after the definition we always put some examples. So here some interesting example we can have, and you may generalize this as here it is written that if you get all binary strings of length k, if you have all binary strings of length k, and then you get a k cube, that is if you And the adjacency relation will be same, that if you have that exactly differing at one place, then they are adjacent, and in that case you will have k degree for each vertex, and so the graph will be k regular. Now we go for some results. The first result is that sum of all degrees of vertices is twice the number of edges. As already we have discussed, there is nothing more to prove here, as you see that including the loop, each edge contributes 2 to the sum of degrees of vertices. If we have a single edge, then it contributes 1 each for its endpoints, and if you have a loop, then it contributes 2 to that vertex. So if each edge, whether it is a loop or not, it is contributing 2 to the sum of the degrees, and so the sum of the degrees is twice the number of edges. So it is very much clear. So this is a simple thing, that this is the first result that in our course we have, that this is the first result, that sum of degrees of vertices is twice the number of edges. But you will see that this result is very simple and immediate from the definition of degrees and the adjacency or incidence of the edge. But many times, and we will use this result in graph theory. Throughout the graph theory, repeatedly we will use this result. And one immediate consequence of this is corollary 1.1.1, where you see that the sum of degrees of all the vertices of a graph is an even integer. This is just obvious, because already we have said that it is twice the number of edges, so sum of degrees must be even integer. But why we are stating this? We are stating this because we will come to another result, and that is the number of odd degree vertices is even. That is a very interesting result, and you see that if you add odd number of odd integers, then you always get odd number. That is a simple property of number theory that you can easily prove, that if you sum odd numbers of odd integers, then always you get an odd integer. So your sum of the degrees of vertices is even. So which are the even degree vertices? If you subtract from them all the sum of the even degree vertices, then it still remains even, right? So the remaining is the sum of odd degree vertices. So sum of the odd degree vertices is even, and that says that the number of odd degree vertices is even. But the result is interesting. The proof is simple and very easy and trivial, you can say also, but the result is very important. So whenever, suppose I am giving some degrees of the vertices, and I am asking you whether these degrees of vertices and whether these degrees of vertices can be possible for a graph that is having these degrees, that we will just come into the degree sequence. Suppose I am giving you a set of integers and asking that whether there exists a graph with this set of degrees, and then if you see that there are odd numbers of odd degrees or odd integers, then immediately you can say that no, there is no such graph drawing is possible, so that a number of odd degree is odd. So the number of odd degrees is even, and that becomes an immediate consequence of the theorem that sum of degrees is even. So this is one result, and then we the similar kind of result in the directed graph also. As I told you that the in neighbors and out neighbors in our previous class. So in the same way, for directed graph we can define in degrees and out degrees. And okay, just let me show you some directed graph. For example, this one. Now you see that in this directed graph, you see that V2 has two out neighbors V3 and V4, and V1 has out neighbor and in neighbor same, that is itself, and V3 has one in neighbor V2 and V4 has one in neighbor V2. Now how we can count in degrees and out degrees? We define in degrees is the number of in neighbors and the out degrees is the number of out neighbors. So V2 has in degree 0 because it has no in neighbor, but V2 has out degree 2 because it has two out neighbors. V3 has out degree 0 and in degree 1. V4 has out degree 0 and in degree 1. V1 has in degree 1 and out degree 1. So in the case of loop, we are consider it as an in neighbor as well as an out neighbor, that is itself. So in this way you can see that if you have any arc has a tail and a head, and tail is the starting point of the arc and head is the finishing point of the arc. Now for the tail it is contributing an out degree, and for the head it is contributing one in degree. So whether it is a loop or not, the arc contributes both one to the in degree and one to the out degree. Each arc, whether it is a loop or not, it contributes one to the in degree and one to the out degree in the sum of in degrees and out degrees respectively of the vertices. So obviously you get this result that that the number of arcs is here exactly equal to the sum of in degrees and sum of out degrees of the vertices. Like in the undirected graph, we said that number of degrees is twice the number of edges. Here the number of in degrees plus out degrees is twice the number of edges, and they are separately equal to the number of edges. এরপরে পরের রেজাল্টগুলো যাওয়ার আগে আমি একটা ইন্টারেস্টিং জিনিস বলি, সেটা হচ্ছে এই বাইনারি রিলেশন এবং তোমার এই ডাইরেক্টেড গ্রাফ, এটা অ্যাকচুয়ালি ডিরেক্টলি লিঙ্কড। কারণ ডাইরেক্টেড গ্রাফ যেভাবে ডিফাইন করা হচ্ছে, দেখো যেটা আমরা আগের দিন আলোচনা করলাম, ডাইরেক্টেড গ্রাফ বেসিক্যালি রিলেট করা হচ্ছে, দেখো যে এজ সেট থেকে ভি ক্রস ভিতে একটা ম্যাপ নেওয়া হচ্ছে। এবার যদি ডাইরেক্টেড গ্রাফটা যদি তোমার কোনো প্যারালাল এজ না থাকে, তাহলে এজ সেটটা কী হয়ে যাচ্ছে, এজ সেটটা জাস্ট ভি ক্রস ভির সাবসেট হয়ে যাচ্ছে। সো ইফ দের ইজ নো প্যারালাল এজেস, there might be loops. Loops are not problematic here, because loop you can represent v comma v. The ordered pair v comma v will represent a loop at v. But if you have several v comma w, so if we want to make them distinct, then we naturally want this incidence function to make them distinct and they have the same image v comma w. However, suppose we are considering a digraph or directed graph without parallel arcs, and then you see that it is nothing but the edge set is nothing but the subset of v cross v. Now we know that from the very basics of our algebra that any subset of v cross v is a binary relation on v. So it is nothing but a binary relation. So any digraph that is without multi-arcs or parallel arcs, that can be represented as a binary relation one-to-one way. That is, there exists exactly one-to-one correspondence of the set of binary relations on a non-empty set V, and the set of all digraphs without parallel arcs you can define on the vertex set V. So, and exactly in the similar way there are interesting digraphs which are reflexive, symmetric and transitive. So when they are becoming reflexive, when we are getting loops at each vertices, and then we get that they are reflexive. Suppose for this graph you see that there are loops at every vertex, so the graph is reflexive here. And exactly we say the term reflexive for the graph also, because the representation is unique for every digraph without multi edges, multi arcs or parallel arcs are uniquely correspond to a binary relation. And in this figure you notice that there is a loop at every vertex, so directed loop at every vertex, and so it is reflexive. And then the property symmetric, here you see that the graph is also symmetric. Now one thing you notice for the digraph, though it is looking in the figure that like a parallel edge, these are not parallel edge, because one edge is suppose from 1 to 2, then another edge is from 2 to 1. These are different because one is representing by the pair 1 2, another is representing by the pair 2 1. So image of this incidence image of this edge is 1 comma 2, and incidence image of this edge is 2 comma 1. So they are different, they are not same, they are not parallel. These arcs are nothing but bidirected. You can say that these arcs are bidirected. And then you see that this is symmetric, but because whenever you get 1 2 you get 2 1, whenever you get 3 1 you get 1 3, and so on. So you see that the digraph is symmetric. And let us see that whether it is transitive or not. Here it is, we have 1 2, we have 2 3, and we have 1 3 also. And so you see that I think it is transitive. You see 2 1 1 3, and you get then 2 3. So it is a transitive graph. You see again that in the other part also there is 4 5 and 5 4. So you have, this is basically corresponding to an equivalence relation. So this graph corresponds to an equivalence relation, and you say that you learned about that equivalence relation forms a partition of the set, and here you see that how they are forming a partition of the set of 5 elements partitioned into 2 parts, 1 2 3 and 4 5, and in each part every element is related to other including itself. Every element is related to other including itself. And so you see that it clearly describes an equivalence relation. It is reflexive, symmetric and transitive, and for the transitive digraphs are very important in the study of digraph. As you know, transitive relation is a very mystic relation that we still could not count by a formula, and transitive digraphs are also very much important in many theories that we will learn later on. So that I am saying that exact one-to-one correspondence between binary relations and digraphs. কিন্তু ডাইরেক্টেড গ্রাফে আমাদের এই পরে যখন আমরা দেখব যে এটাকে তুমি ম্যাট্রিক্স রিপ্রেজেন্টেশন করতে পারো, এটা এখনও বুঝতে পারছো যে আমরা যেহেতু এটা বাইনারি রিলেশন বলছি, তাহলে অবভিয়াসলি আমি এখানে একটা ম্যাট্রিক্স রিপ্রেজেন্টেশন করতে পারি যে আমার ইউ কমা ভি যদি থাকে তাহলে ইউ ভি এর পজিশনটা আমার 1 হয়ে যাবে, আদারওয়াইজ ইউ কমা ভি না থাকলে ওটা 0 হয়ে যাবে। তাহলে সেই যে ম্যাট্রিক্স রিপ্রেজেন্টেশনটা আমরা করি, এই ম্যাট্রিক্সটার এই রিফ্লেক্সিভ কখন হবে? যখন টোটাল ডায়াগোনালটা 1 হয়ে যাবে। এবার আমরা দেখব যে ডায়াগোনালটাকে আমি যদি লুপ না রাখি তাহলে টোটাল প্রিন্সিপাল ডায়াগোনালটা 0 থাকবে, আর যদি লুপ প্রত্যেকটা ভার্টেক্সে রাখি তাহলে রিফ্লেক্সিভ হয়ে প্রিন্সিপাল ডায়াগোনালটা সবকটা 1 হয়ে যাবে। এবার আমরা দেখি যে বেশিরভাগ কেসে যখন ডায়াগ্রাফের ওই ম্যাট্রিক্সটার বিভিন্ন প্যাটার্ন আমরা কনসিডার করি, দেখা যায় যে ম্যাট্রিক্সটা খুব ইন্টারেস্টিং কতগুলো প্যাটার্ন নিচ্ছে, মানে 1 0 কতগুলো অ্যারেঞ্জমেন্ট নিচ্ছে, যেটা একটা সিমেট্রিক প্যাটার্নের মতন। সেই প্যাটার্নগুলো বা সিমেট্রিক বা অ্যাসিমেট্রিক, যাই হোক সাম প্যাটার্ন উড বি দেয়ার। এবার সেই প্যাটার্নটায় সুবিধে হয় যদি আমরা প্রিন্সিপাল ডায়াগোনালটা 1 রাখি, তখন আমরা ওই প্যাটার্নটাকে এক্সপ্লেন করার জন্য বা প্যাটার্নটাকে এস্টাবলিশ করার জন্য রাদার, তখন আমরা সবকটা ভার্টেক্সের লুপ অ্যাসিউম করে নিই। সিম্পল ডায়াগ্রাফই ধরছি, বাট অ্যাসিউমিং যে প্রত্যেকটা ভার্টেক্সের লুপ। ফলে রিফ্লেক্সিভ ডায়াগ্রাফটা বেশি ইউজ করা হয়, মানে রিফ্লেক্সিভ ডায়াগ্রাফটা আমরা অনেক ইউজ করি, আর প্যারালালটা খুব কম ক্ষেত্রেই আমরা ইউজ করি। কিন্তু ডেফিনিশনটা অবশ্যই আছে এবং আমরা ডিফাইন করতে পারি মাল্টি ডাইগ্রাফ, এবং ইন জেনারেল ডিফিনিশনটা তাই, মানে ইন জেনারেল ডাইগ্রাফ বলতে মাল্টি ডাইগ্রাফ। এবার তার একটা স্পেশাল কেস হচ্ছে এই সিম্পল ডাইগ্রাফ। আর তুমি যদি লুপ নিয়ে নাও তাহলে তুমি জাস্ট বলে দিলে যে রিফ্লেক্সিভ ডাইগ্রাফ আমি ধরছি, বাট উইদাউট প্যারালাল আর্কস। তার মানে লোকে বুঝে নিল যে হ্যাঁ ঠিক আছে, রিফ্লেক্সিভ ধরা হচ্ছে উইদাউট প্যারালাল আর্কস। নাও উই গো ফর দ্য সাবগ্রাফস। So like every structure has, the important thing is that what is its substructure. Whenever you have learned groups, we have learned subgroups, rings, subrings, and so on. And you notice that in the case of groups and rings, not only we restricted ourselves by defining subgraphs, but also we were keen to designate some special kind of subgroups as normal subgroups, or in the case of rings, special kind of subrings as ideals, and which are basically connected with the homomorphisms. And here also there are two concepts, subgraphs and the induced subgraphs. First of all, what is a subgraph? In the case of subgraph, we naturally we have that the vertex set of the subgraph is subset of the vertex set of the original graph, mother graph, and the edge set is also the subset of it. That is, you see that there is a graph G here. Look at the graph G1 just beside it, and you see that all V1 to V5 are vertices of G. So this is a subset of G, and this E1, E2 and E4, they are also in E, and so they are subset of E. So the important thing for forming a subgraph, you see that there is no edge between V2 and V6 in the original graph. So there is no edge, there cannot be any edge in any subgraph between V2 and okay, here it is V5. So you see that if I draw an edge from V2 to V5, so that is not permitted for subgraph, because that edge is not in the original mother graph. So we cannot take the edge, we can only take the edge which are present in the mother graph. Now on the other way, so if we have an edge in a subgraph, so its endpoints must be the same as the endpoints in the mother graph. That is very much important, because not only you are saying that E subset of E and V say E1 subset of E and V1 subset of V, and then V1 E1 is a subgraph. That is not. You must write that for every edge E, that G of E, if it is V1 comma V2, then in the original graph also G of E must be V1 comma V2. So here the incidence function is obviously a restriction of that of the mother graph, that if I call it G1, then G1 is a restriction of G, but they are giving you the same set of images here. So you see that various subgraphs are given here, but in the subgraph you see that not all the vertices are there. Yeah, for G3 there is a distinction between G3 and these two graphs G1 and G2. Can you notice that distinction? মানে G1 আর G2 G3 থেকে একটু আলাদা। কোথায় আলাদা? যে ভার্টেক্সগুলো নেওয়া হয়েছে, যেমন দেখো এই যে G1 এ, হ্যাঁ দেখো V2 আর V3 এজটা কিন্তু মাদার গ্রাফে আছে, আর এখানে V2 V3 দুটো ভার্টেক্সই নেওয়া হয়েছে, কিন্তু সেই এজটা কিন্তু এখানে নেই। কিন্তু G3-তে দেখো চারটে ভার্টেক্স নেওয়া হয়েছে, এই চারটে ভার্টেক্সের ইন বিটুইন যতগুলো এজ ছিল সেই ততগুলো এজই এখানে কনসিডার করা হয়েছে। মানে সাপোজ এখানে আমি যদি E3টা না নিতাম, V3কে আইসোলেট করে দিতাম, তাহলে এটা ওদের মতোই হতো যে আমি ওর কিছু এজ সিলেক্ট করছি। সো অ্যাকচুয়ালি G3 ইজ দ্য ইনডিউসড সাবগ্রাফ অ্যান্ড G1 আর G2 আর অর্ডিনারি সাবগ্রাফস। মানে এটা এখানে ওই নর্মাল সাবগ্রুপ বা আইডিয়ালের মতো হয়ে যাচ্ছে, এটা স্পেশাল সাবগ্রাফ, এটা ইনডিউস সাবগ্রাফ। আর ওটা হচ্ছে ওইগুলো হচ্ছে G1 G2 হচ্ছে অর্ডিনারি সাবগ্রাফ। অর্ডিনারি সাবগ্রাফ আর ইনডিউস সাবগ্রাফের মধ্যে ডিফারেন্সটা কি? ইনডিউস সাবগ্রাফ হচ্ছে হোয়েন এভার ইউ আর টেকিং সাম ভার্টেক্স সেট, you must have to take all the edges between them, those are present in the original graph. মূল গ্রাফে ওই ভার্টেক্সগুলোর মধ্যে যতগুলো এজ আছে তোমাকে সেগুলো নিতেই হবে। যদি তুমি সেগুলো নাও তাহলে সেটা আমরা বলবো দ্য গ্রাফ ইনডিউসড বাই দ্য সেট অফ ভার্টিসেস। এটাকে আমি ইনডিউসড বাই দ্য সেট অফ এজেসও ডিফাইন করা হয় আপাতত, কিন্তু ইনডিউসড গ্রাফ বলতে আমরা জেনারেলি ইনডিউস সাবগ্রাফ বলতে ভার্টেক্সটাই মিন করি, আমি পরে এজের ব্যাপারটায় আসছি। তা আপাতত এই ডিফারেন্সটা দেখো, এখানে G2 কেসেও দেখো V1 টু V6 একটা E7 এজ মাদার গ্রাফে আছে, কিন্তু এখানে সেটা শো নেই, তার মানে এখানে ওই এজটা নেওয়া হয়নি। ফলে বোথ G1 অ্যান্ড G2 দিজ আর অর্ডিনারি সাবগ্রাফস, but G3 is an induced subgraphs. So these are the differences. So we come to the language, that is the formal definition. You just see that how we define a subgraph, that if G is a graph VEG, then G1 is called a subgraph of G, and G is called other way the supergraph of G1. However, we seldom use the supergraph language, mostly we use subgraph. If V1 is a non-empty subset of V, E1 is a subset of E, and G1 is the restriction of G to E1 such that for all E belongs to E1, G1 of E equal to G of E equal to U comma V, then U comma V belongs to V1. That is extremely important. You can think that why we are forcing that thing, but because you see that you are considering some age, but whose endpoints you are not considering in the subgraph, then it is meaningless to draw that or consider that subgraph. তুমি তো সেই গ্রাফটাকে আঁকতে পারবে না, আর সেই গ্রাফটা কোনো মানেও থাকবে না। মানে তুমি শুধু এজটা নিলে, তার এন্ড পয়েন্টগুলো নিলে না, তাহলে সেই গ্রাফটার কোনো অর্থ থাকবে না সেই এজটার। ফলে এটা রেস্ট্রিকশন বলাটাই সাফিসিয়েন্ট না, ইট ইজ নট সাফিসিয়েন্ট যে তুমি বলছো G1 ইজ দ্য রেস্ট্রিকশন অফ G, কারণ তুমি যে ভার্টেক্সগুলো চুজ করছো তার মধ্যেই যেন এই E1-এ যে সব এজ চুজ করছো তার এন্ড পয়েন্ট সেটটা থাকে। দ্য এন্ড পয়েন্ট সেটস অফ E1 মাস্ট বি দ্য সাবসেট অফ V1, এইটাই হচ্ছে বক্তব্য। এটা করলে তারপরে রেস্ট্রিকশন বললেই হয়ে যায়। মানে এই ডেফিনিশনটা আমি এভাবেও বলতে পারতাম যে ওই ইউনিয়ন অফ জিই ই রানস ওভার E1 সাবসেট অফ V1, এটাও আমি বলতে পারতাম যে ইউনিয়ন অফ G1 ই রানস ওভার E1 ইজ সাবসেট অফ V1, সেটা বলা যায়, এটা বলাও তাই, কারণ ওই রেস্ট্রিকশন বলে দিচ্ছি বলে ব্যাপারটা এন্ড পয়েন্টগুলো সেমই থাকছে, এই G1 ইকুয়াল টু জিই হয়ে যাচ্ছে। দ্যাট কামস ফ্রম দ্য রেস্ট্রিকশন ডেফিনিশন, কারণ আমরা একটা ফাংশনকে কখন রেস্ট্রিকশন বলি, যখন তার একটা সাবসেটের উপর ডিফাইন করা হচ্ছে কিন্তু ইমেজগুলো সেম থাকছে। এখানে সাবসেটের উপর ডিফাইন করা হলো, ইমেজগুলো সেম থাকলো, কিন্তু এটাও আমরা বললাম যে ওই ইমেজের এলিমেন্টগুলো যেন ভার্টেক্স সেটে নেওয়া হয়, না হলে এটা মিনিংফুল হবে না। আর ইম্পর্টেন্ট হচ্ছে যেমন আমরা প্রপার সাবগ্রুপ বলতাম, এখানেও আমরা প্রপার সাবগ্রাফ বলছি, যে তার মানে যেটা অরিজিনাল গ্রাফের সঙ্গে ইকুয়াল নয়, আইদার একটা ভার্টেক্স মিসিং আছে অথবা একটা এজ মিসিং আছে, তখন আমরা ওটাকে প্রপার সাবগ্রাফ বলছি। আর এরপরে আমরা ইনডিউস সাবগ্রাফের ডেফিনিশনটা দেখো, যে এখানে বলা হচ্ছে যে G be a graph and U be a non-empty subset of V. Let G1 equal to V1 E1 be a subgraph of G, and then G1 is called a subgraph induced by U if V1 equals to U, E1 equal to E belongs to E, and vertices of E are in U. If G1 is induced by U, then we say that G1 is GU. মানে যে এজগুলো নেব ও সেই এজগুলোই আমি নিচ্ছি যেখানে কিন্তু তার এনভার্টেক্সগুলো ইউতে আছে, সেই সবকটা এজ আমি নিয়ে নিচ্ছি। মানে E1 এর ডেফিনিশনে দেখো E বিলংস টু E, হোয়ার এনভার্টিসেস অফ E আর ইন ইউ। এই ইটা আমরা কোত্থেকে আনছি, ক্যাপিটাল ই থেকে আনছি, ফলে মাদার গ্রাফেও এজটা আছে, এবং মাদার গ্রাফে যেসব এজ আছে সবকটাই নেব যদি তার এন্ড পয়েন্টগুলো এই ইউতে থাকে, তাহলে সেটাকে আমরা বলছি সাবগ্রাফ ইনডিউসড বাই দ্য ভার্টেক্স সেট ইউ, রাইট। এখন যতগুলো সাবগ্রাফই আমরা একটা ফিক্সড ভার্টেক্স সেট নিয়ে আঁকতে পারি, তাদের মধ্যে অবভিয়াসলি ইনডিউস সাবগ্রাফটাই ম্যাক্সিমাল হবে, কারণ ওখানে আমরা সবকটা মাদার গ্রাফের এজই নিয়ে নিচ্ছি, আর মাদার গ্রাফের এজ ছাড়া অন্য কোনো এজ আমরা কোনো সাবগ্রাফেই নিতে পারছি না। ফলে এজেসের দিক থেকে এটা অবশ্যই ম্যাক্সিমাল হয়ে যায়। ফলে দ্য ম্যাক্সিমাল সাবগ্রাফ কন্টেনিং দ্যাট ভার্টেক্স সেট, এটাই ইনডিউস সাবগ্রাফ হয়ে যাচ্ছে। উই ক্যান ডিফাইন ইন দিস ওয়ে অলসো। ভেরি গুড, ইটস অ্যান অল্টারনেটিভ ডেফিনিশন। নেক্সট হচ্ছে আমরা এখানে দুটো অপারেশন আমরা আমাদের নিজেদের সুবিধার জন্য আমরা তৈরি করছি, যেটা হচ্ছে একটা গ্রাফ থেকে একটা ভার্টেক্স আমরা ডিলিট করা বা একটা এজ ডিলিট করা, এটা বলতে আমরা কি বুঝি, যে হাউ উই ক্যান symbolize or we can make the notation that deleting a vertex from a graph. Now as you are seeing on the screen that it is written that G minus singleton set V. So the resulting graph we write G minus singleton set V in this way. That means that we have deleted the vertex V from the graph. But when we are deleting a vertex from the graph, actually we have to delete all the edges incident with V. Otherwise you see that we have to delete all the edges incident with V. Otherwise these edges would not be meaningful, because for these edges V is one of the endpoint. V থেকে কতগুলো এজ বেরিয়েছে, এবার ভিটা নেই, এজগুলো তো নিরলম্ব শঙ্কু হয়ে ত্রিশঙ্কু হয়ে ঝুলতে পারে না, তাহলে ওদের তো এন্ড পয়েন্ট লাগবে, তাহলে সেই এজগুলো অটোমেটিক্যালি ওখানে ক্যান্সেল হয়ে যাচ্ছে। ফলে একটা গ্রাফের কোনো ভার্টেক্স যদি আমরা ডিলিট করে দিই, তাহলে ওই ভার্টেক্সের সঙ্গে যা যা এজ ইনসিডেন্ট ছিল সেগুলোও কিন্তু সব ডিলিটেড হয়ে যাচ্ছে। অল দ্য এজেস ইনসিডেন্ট টু ভি উইল বি ডিলিটেড, বাট ইন দ্য কেস অফ এজেস দিস ইজ নট, because if we just delete an edge, we delete an edge, the vertex set will remain the same. Even if the vertex set becomes, some vertex becomes isolated, then also it remains the same, just we drop the line, just to erase that line. And that is the definition of deleting the edge. What is here is symbolizing G minus C. When we are making G minus C edge deletion, so it is only edge deletion, there is no vertex deletion. But when we delete the vertex, unless it is an isolated vertex, so it will delete many edges. So suppose from this graph G2, if we delete the vertex V6, there is no harm in it, there is no edge will be deleted. But if we delete V5, then you see that both E5 and E6 vertices, those will be deleted. So the graph remains V1, V2 and V4 and the singleton V6. So ফলে V5 যদি আমি ডিলিট করে দিই, তাহলে কিন্তু E5, E6 দুটোই গ্রাফ থেকে চলে যাবে। তার ফলে ওই V1, V2 আর V2, V4 ওই এজগুলো থাকবে, আর V6টা আইসোলেট থাকবে। এই এপাশের যে E5, E6 এটা বেরিয়ে চলে যাবে গ্রাফটা থেকে, V5টা যদি আমি তুলে নিই এখান থেকে। So these are the just deletion notation. So the last thing that we will learn today, that is simple graph. And simple graph is a graph without any loops or parallel edges. এখানে কোনো লুপ নেই, কোনো প্যারালাল এজ নেই, সেই গ্রাফগুলোকে আমরা বলছি সিম্পল গ্রাফ। এবং এই সিম্পল গ্রাফে ডেফিনিশনটাও সিম্পল হয়ে যাচ্ছে, মানে সিম্পল গ্রাফে আমরা আমাদের ওই ইনসিডেন্স ফাংশন আনার কোনো দরকার নেই, কারণ এখানে কোনো মাল্টি এজ নেই। তা পরিষ্কার আমরা একটা নন এমটি সেট নেব, সেট অফ ভার্টিসেস, আর ওই ভার্টেক্স সেটের কতগুলো টু এলিমেন্ট সাবসেট নেব, a collection of two element subsets of V, and that is basically E. If E is empty, then it is empty, but it is just a subset of all the two element sets of V. So it is in this way simple graph you can represent by just an unordered pair, a collection of unordered pairs of vertices. So in this way you can easily represent a simple graph. And our most of all study of the graph theory we will make on simple graphs. Now you can remember that in our previous class we have started our course with this simple puzzle or simple problem, that in any gathering of n greater than 1 people, there are at least 2 people who have same number of friends. And that is the same thing that is written here in terms of graph theory, that let G be a simple graph with at least 2 vertices, then G has at least 2 vertices of the same degree. I think I don't have to any more discussion about that for the proof. The proof, you know that the degree of the vertices, now you know that the number of lines those are incident to a vertices is a degree, and there are no loops here, no multiple edges here. So any graph, those are with the lines incident on it, those are just the degrees of the vertices. So the graph has the number of lines exited as same as the degrees. So it is the same way that we can say that for a simple graph, the minimum degree can be 0 and the maximum degree can be n minus 1. If there are n vertices, since it is a simple graph, one vertex can be adjacent to only other n minus 1 vertex, no loops are here. So degrees can be from 0 to n minus 1. But if we have a vertex of degree 0, that is an isolated vertex, then no vertex can have degree n minus 1. So either the degrees from 0 to n minus 2 or the degrees from 1 to n minus 1. So you see that here it is either the set is 0 to n minus 2 or the set is 0 to n minus 1. And so these are the n minus 2 numbers, n minus 1 numbers, and that you have to place in for n vertices. And so it is simple PHP, that P general principle, that 2 vertices of the same degree. However, it is again the simple result gives you another intuitive idea that when you are going for the degrees of vertices, and then you can have, if I give you some integers where the some set of some non-negative integers, and asking that whether a graph is possible having the degrees of the vertices like this, and then if you have that all the numbers are distinct, and immediately you can say there cannot be any simple graph. There cannot be any simple graph of this with these degree sets. So this is the one implication of this. Okay, we stop today's lecture.